Bismillahirrahmanirrahim. I am Usman Javed and this is a determinate structure analysis course. In this lecture we will discuss about the virtual work method in case of trusses. These are the contents of this lecture, and we will discuss the external work done by the response of which there is some internal strain energy which acts upon, and some work done is performed internally, and then we will discuss the principle of work and energy, relation of a principle of work and energy, and then we will discuss the principle of virtual work, um, and then solve some example of a trusses by virtual work method. Basically, when any external force acts upon some structural elements, it would cause some deformation, some rotation, some deflections. So by the action of that applied force there is a deformation. So external work done, we can say that um, the work done is performed upon the structure when the externally applied load is acts upon it and cause some deflection or rotation something. So external work done can be taken as so the external work done would be related to the externally applied force. What would be the internal work done? When the force is applied, there must be some strains, there must be some resistance to the external work, resistance to the applied loading. So the external work done can mathematically can be written as in the form of a strain energy UE. uh, UE UE equals to F times delta X. This is for example, we have a structure, we have an element with the length L upon which the force F is applied, and there is a deformation delta by virtue of this applied force F, and then there's a function, there's a graph of F and X. F is basically applied force and X is a deformation. So delta is a very small deformation upon it. So in terms of external work done, what we can say that the external work done can be written as delta UE equals force times displacement. So this line, basically this curve shows the uh, force. So what we can see from this graph that the force is gradually increasing the deformation upon the structure. So when the force increases, the deformation increases linearly. So we can write the force in terms of deformation, like P over delta into X, and we can integrate this function up to the total length of um, uh, um, we can integrate this equation up to the total of the deformation which has been occurred. So external work done would be like half of P into delta. So simply we can say that if externally force applied on upon the structure, there is some deformation with the action of that force. So that external work done can be calculated as half of P delta. P is applied force, and which is gradually increasing the deformation by increasing the value of force. So the delta is the deflection due to that force. So it is a basically external work done. So for example, we have a 20 kilonewton load acting upon it, and there's a 1 centimeter of a deflection, so 1 centimeter of a elongation caused in that bar element. Then we will if we draw the graph of force delta graph, if we draw the force delta graph, we can see that with a maximum value of 20 kilonewton, there is a maximum deflection elongation of 1 centimeter. So we can calculate the external work done due to the action of that force. So external work done will be like half of delta into P, which is 100 Newton meter. So if we talk about the internal work done, which is done by the structure in the response of that applied loading, it would be like we have a structure, we have a bar element with the length L, and the force acts upon it, whose value is N, and there is a deformation delta. If we draw the stress strain diagram, basically stress strain diagram is the internal response of the structure to the external loading. So we will consider here the stress strain diagram instead of a P delta curve. P delta curve is basically the externally apply, basically the action or a function of a externally applied loading. In case of a internal work done or a strain energy within the structural element, we'll discuss about the stress strain curve. So what we can say that internal strain energy or internal work done can be calculated as integration of a u dot. What u dot is? U dot is basically uh, u dot is basically half of stress into strain, which is the slope of this curve, up to the extent where the linearity of this curve exists. So the internal strain energy within the linear limits or a elastic limit can be written as half of delta strain. So keep in mind this strain energy is valid up to the elastic limit. So we can write the over internal strain energy as half of stress into strain, which is the slope of this curve, of this linear curve. We can also write the modulus of elasticity equals stress over strain, which comes from the Young's modulus. So we will compute the value of epsilon, which is strain, basically value of strain, into the equation, which will transform like stress square sigma square over E. Then we'll compute the sigma equals N over A. N is basically the axial force upon the bar element, and A is its cross sectional area. If we compute this relation within this equation, we'll come up with this formula with the, and finalize it as n square over 2 EA. Basically n square is the normal force which acts upon the structure, and EA is stiffness of that bar element, and that limits is from 0 to L, 0 to whole length of that element. So this is basically the internal strain energy for the bar elements, for the truss elements, you can say. If we talk about the internal strain energy within the flexural element like beam, we will consider it like by computing the flexural formula into the equation, into the basic equation of a into the basic equation of a strain energy. So strain energy was u naught into with the differential of a dv, which is integrated up to the whole length L. So we will compute the value of u naught in terms of flexural elements. So u naught can be computed as half of stress into strain. Then strain is replaced by the stress over E, like we have done it for a bar element. Then we will replace this amount of stress with the stress value in a flexural formula that we have calculated in a mechanics of solids, which comes out as flexural strength would be would be calculated from the flexural formula, which was derived by this hypothetical curvature of a bending, which comes out as stress equals to my over I. Stress equals to my over I. Flexural stress equals m is basically the moment, y is the distance from neutral axis to the extreme fiber, and I is the moment of inertia of that cross section. So we will compute F equals my over I up here. So the stress can be written as my over I whole square. Delta V is the value of a shear equals to area into dx, the area of this cross section into dx. Basically delta V is transformed into dA into dx by taking sigma f of y equals 0. So dA and dx is cumulative function of a vertical force acting upon this cross section. So delta is a whole area, and delta x is basically the small chunk of this cross section. So delta A into delta x is a total shear acting upon it. So we can transform delta shear into delta A into delta x. So the limits are now changed. We can write it as a first moment of area, this y square as a first moment of area, which is moment of inertia. So we can write it as m square into I over 2 ei square. So finally it can be written as m square over 2 ei with the limit reaches from 0 to total length of that beam. So this is a finalized equation. Basically these equations are derived from the mechanics of solid course. You can go and search the mechanics of solid by Singer. So this is a book, mechanics of solid by Singer, 4th edition, page. So you can search all about these proofs up there, over there. So in case of a torsion, what would be like internal strain energy? We are considering the axial forces, we are considering the flexural forces for beam elements, we are considering the torsional forces to calculate the internal strain energy for all of these elements we will be solving in our course. So the modulus of torsion, modulus of rotation has been changed, which is half of tau into gamma. Basically tau is basically it's a sustained diagram of a shear strength, and gamma is basically the rotation or twisting, and tau is a shearing stress. How the shearing stress affects the twisting of that bar element. We can compute the internal strain energy as a half of tau gamma, and G, which is the modulus of torsional modulus, which is basically the slope of this linear curve, this elastic curve, which can be equated as tau over gamma. Like we have a Young modulus, which is a ratio between the stress into strain. So the gamma can be computed as tau over G, which comes out from the torsional formula. You can see the proof of a torsional formula from this book, Strength of Material by Singer. We are not going to have a look over the proof of this tau. In this equation there is a shear strength, and this is the torsional force T, and we have a J. Rho is basically the radial distance. So you can compute the value of tau into the formula, and you can calculate your final strain energy into the torsional. In case of a torsion, it comes out as T square over 2JGJ. For in case of a shear, you can calculate the shearing stress. You can compute the shearing stress, and then compute shearing stress into the this very famous formula. You can calculate the internal strain energy due to the shear. Basically, you have in shear, what you have is basically the shearing stress tau and the rotation gamma. You will compute the value of a u first, and then compute the value of a g, which is tau gamma, and you have an equation like this, which is half of tau square over g, and then you will compute the value of tau square from this derivation of a shear strength, which is tau equals vq over it. V is a shearing force and shear force, q is a shear flow, and I is moment of inertia, and t is the thickness of that cross section. So you can compute this tau into the u formula, into the internal strain energy formula, and then compute the values. Like you have a v square over 2 ga. So internal strain energy can easily be calculated as these formulas for rotation, shear, and bending. So for example, we have a cantilever beam with the length L and P force acting upon the free end of a cantilever beam. So we can calculate and make calculate the deflection by means of a virtual work method. So how its moment diagram would look like. It would have a maximum shear at the support because it's a cantilever beam, and the minimum at free end. The value of moment would be P times L if we taken the counterclockwise moment as a positive, so PL would be negative. If we draw the cross section at some distance x, it would be like V, and the moment V is coming downward. You can change the trends, and you can change the convention of a moment and shear. There are two convention follows. It can be like but keep in mind that what the convention you have said, you will follow it throughout your problem, so that it would not change or changes your results. So we have a convention like shear is going downward and moment is acting thisward. Basically these are the assumed directions. If we have actual values comes negative to that value, then we can correct it afterwards. So we can say that these are the assumed values. P is externally applied load with the distance x from the free end. The V is a virtually or internal force of internal shear force and internal moment. You can calculate the shear force and moment by taking the moment at point x, which is some arbitrary point. Like you can take the moment at this point equals 0, then P into x would be treated as a negative, because we have a convention of a counterclockwise as a positive. It's also clockwise, so it would also taken as a negative. So you have a moment comes out as negative of px. The internal strain energy in this case would be as we have a equation that the external strain energy equals to internal strain energy. This is a virtual work method, which is basically the external applied load causing the external work done, and there is some hindrance, there is some strength within the structure to resist the external loading by the action of some internal thrust. So external applied loading caused deflection or some rotation. So the external applied forces causes the deflection, which can be calculated by the external work done, which is half P delta, and internal strain energy can be calculated in the form of this formula which we have derived earlier. This is basically for the bending or purely flexure case, in which we have a m square dx over 2ei. M is a moment at some m is a moment value. EI is a stiffness, flexural stiffness of this beam. You can and the limit is 0 to whole length of this cantilever beam. So you can calculate, you can compute the moment value, and you can make the equation like half P delta equals P is externally applied load P square into you will integrate the value of x up to the limit 0 to L, which is the whole length of a cantilever beam. So you have a delta value, which delta value for a flexural case like delta equals PL cube over 3EI. So you can calculate the delta value of a delta by principle of work and energy principle by delta equals PL cube over 3EI. First, you have computed the external and internal strain energy. You have computed the external applied loading, the effect of a work done by external applied loading, and then you have computed the internal work done, which is basically due to the moment or rotation. uh, then you have computed the moment values and come up with the generalized equation in terms of a loading and length of a beam. So you can calculate the deflection uh, in this way. So so the virtual, what is the virtual work? Previously we have discussed about the principle of work and internal energy, strain energy, then calculate the deflections and deformations into some structural elements. Then now we will discuss the virtual work method, what virtual work is. In virtual work method, what we do is we apply the hypothetical value, some unit value loading upon the structure, and then calculate the internal forces and external forces, and we can scale the internal and external for calculated response of a structure or some deformation of a structure by multiplying the unity with the some loading that your structure is experiencing in real time. So which the concept behind the virtual work method is, first you have to calculate the principle of virtual work is basically, first you have to calculate the deformations and deflections by applying the unit load, and then then transform your deflections and any type of a response of a structure by multiplying your applied forces. First we have applied the p load upon the structure, which is virtual, which must be some unity value. It is easy to transform your response of a structure by multiplying the unity value with the actual loading afterwards. Then there is some real load P1 acting. So there is a change in length, and change in length or a strain occurred and the object by the action of that real-time load. You can calculate the delta or a strain by multiplying your P1 with the virtual loading. So here is a delta load, delta internal energy and delta external energy and delta internal energy. What basically delta is? Delta is amount of a work done increased by the action of a force when the force has been applied, when the virtual force has been applied. So we are considering it as a bar element. So internal work done would be like N over EA, something like this, and you have external work done and internal work done equals 0. If we compute the internal work done and external work done can be negated if we assume that there is no loss of energy by transforming the external and internal work done, we can cancel it with each other, because uh, if we assume if we assume that there is no loss of energy by transforming the external work into the internal strain energy, then we can cancel with each other. So on the whole equation comes out as 1 into delta equals sigma u into delta L. So 1 is a virtual loading which was applied upon the structure, a structural element. Delta u is a virtual loading. So the delta is a real time displacement, and delta L is internal displacement. In a similar manner, we can calculate the deflection in terms of a rotation. So, if we talk about the virtual work in case of a truss elements, we'll apply some virtual load of some unit value and then transform your then calculate its deflections. For example, we have a external we have a virtual work of 1 kilonewton acting upon the B value B point or a joint in a truss element as shown. You can calculate the value of a response of a structure. Either the each member is going in compression or a tension. Basically, it's a response to that virtual loading. So you will calculate the n1, n2, n3 up to n9, which is a response of a structure or a bar element in terms of by the virtue of externally applied unit virtual load. So you will calculate the compression and tension in the elements by 1 kilonewton applying virtual work, and afterwards you will apply the real time loading, which can be as a P1 and at P2 at different joints and different directions. Then you will calculate the response of a structure in terms of amount of a tension and compression on each elements. So it comes out as n1, n2, n3 and up to n9. How the virtual work can calculate the amount of a deflection delta at point B? Here comes the catch. If you want to calculate the amount of a deflection at any joint, you will apply the virtual load at that node, that particular node. For example, I was interested in calculating the deflection up to at this point B, at this node B. So I have applied the virtual load of 1 kilonewton at that point. So we can calculate the deflection delta by the equation that we have already been developed for the bar elements. Basically, it's a sigma of n, small n, which is the amount of a tension and a compression due to virtual load, and capital N is basically the response of a truss elements or a bar elements due to real-time applied loading. L is basically length of each element that you are calculating, then summing up all the effects of internal and external applied loading and multiply with the whole length. You can calculate the amount of a deflection at point B by applying this formula. So you have one is a external virtually applied load at the point B. It would cause some deflection delta, which would be calculated by this formula, and is a virtual normal force in a truss element or a response of a truss element by the virtue of externally applied virtual loading. Then you have a delta deformation at the point B. Then you have a normal force of a real-time loads or real loads. Length L is the length of each bar element or a truss element. A is a cross-sectional area. E is a modulus of elasticity. AE is basically the stiffness of that bar element. Then you will calculate the amount of deflection at point B easily from this formula. We will solve the real-time examples. So in case of a temperature, you can calculate your response of a structure or a delta in terms of n into coefficient of a temperature alpha into temperature gradient and multiply with the length. You can calculate it is easily. A is basically the alpha is a thermal coefficient of expansion, because thermal coefficient of expansion is basically in the material properties, which varies by varying the type of a material. So it is multiplying with the temperature gradient to come up with the amount of a delta due to temperature gradient or a temperature change rises. So for the fabrication error, for example, you have made your stress elements, but there is some deformation, there is some settlement upon the support, and due to this settlement, the stresses are being transformed into some internal forces like compression and tension. Then you can calculate the amount of a deflection by that fabrication error by means of this formula. So this formula states that a unit deflection is applied, and then calculate the response of a structure by unit deformation in terms of some settlements, in some terms of some change in terms of some change in length. So you can calculate it like n multiplied by change in length. Here is an example to solve the to calculate the displacement at point C when you have a 4 kilonewton force applied at that point. Here is the truss, basic truss, which has a height of 3 meter, and which makes a isosceles triangle with a span of 8 meters. So we have a material properties, a cross sectional area, and modulus of elasticity as here. So we can calculate the amount of a displacement at point C easily by calculating from the principle of a virtual work formula, which is basically small n into capital N multiplied by length divided by stiffness of a bar element, and which is integrated till the whole length of a elements, and for all these 3 elements. So we can calculate it very easily. So you have a virtual work force force of N acting upon a point C. We want to calculate the joint displacement at point C of a vertical 1 kilonewton load. So we have applied the 1 kilonewton vertical virtual load, and then we will calculate the response of these bar elements, 3 bar elements, by the application of 1 kilonewton virtual load. So we can calculate the reactions very easily by applying the sigma f of y equals 0. You will come up as 0.5 and 0.5 kilonewton forces acting upward at supports. As there is no horizontal force, there is ax component would be 0. So by the method of a joint and a section, you will calculate the response of each bar element. You can take the joint A, then joint B, then you can apply the sigma f of y equals 0, sigma f of x equals 0. Then you can have a value of these forces, member forces. Minus value shows that the member is in compression. I have solved the truss element earlier in this course, so you can go over there and learn how we can determine the member forces or a member response. So in this example, I will not go into the detail how to calculate the reaction, how to calculate the member forces. I will just go on with the principle of a virtual work. So after the application of a force, after the application of a virtual force, we will apply the real time force, which is 4 kilonewton, which is acting rightward at point C. So we will determine the reactions upon the support. These are the reactions. How you can calculate the reaction? You have a 2 unknowns. You have basically the 3 unknowns, 1, 2 and 3, and you have 3 equations of equilibrium, which are basically sigma f of x equals 0, sigma f of y equals 0, sigma moment at any point equals 0. Then you will come up with the value of all 3 unknowns. So you have a you have a response of a bar elements by the application of that 4 kilonewton force, which is negative 2.5, 2.5 and plus 2.5. So you will compute the values of bar values of this response of bar elements into the equation, which is basically small n into capital N divided by stiffness multiplied by whole length. So if we discuss it graphically, then we can see that there is a cumulative effect of virtual load and real time load, and this might be transformed into some uh, you know the equivalent of a virtual and externally applied load. Then you will multiply the length up to the members, then the equation would be like this, and you will compute the n capital N into L component into the equation, and the value of delta C delta at point C would be calculated as 0.133 millimeters. So this was a very simple method to determine the deflection in a bar element by the formula of a virtual work method, which we have derived earlier. So in case of a there is a fabrication error, there is some change in length, 5 millimeter change in length. You can determine the amount of a deflection at point C. So in this case, what you will do is, you have a formula of small n into L, sigma small n into L. Small n is a response of each element by the application of a virtual load, and L is deflection, or L is change in length. So you will compute the value of delta L into this AB element. Then you can see that there is a deflection of 3.33 millimeters upward due to this support due to some 5 millimeter shortage of this length AB. So minus values shows that it is going in upward direction. As our supposed direction was downward, it is negative, it means it would be upward, in upward direction. So the support C would face the upward deformation. So if we cumulate the fabrication error, and if we cumulate the effect of a fabrication error and externally applied force, then it would be as 0.133 minus 3.33. The support C comes down with a value of 0.133 due to application of a 4 kilonewton force, and support C comes downward with the application of some fabrication error. So its a cumulative value would be like minus 3.2, which is basically the upward direction. So we can calculate the deflection at point C for this example as well. So I will go through this example very fast. You can solve it by your own time. So we want to have a displacement at point C. So we can easily calculate the amount of a displacement at C point. You have a externally applied loading, you have a truss element with stiffness of E and A, and the dimensions are written over here. You will apply the normal force or some virtual force at point C, and then record the internal forces within the bar element. First you will calculate the reactions, then internal forces, then apply the real loading, then calculate the reactions for that real loading, and you will take the you will solve it by the joint method or section method to calculate the internal forces of a bar elements. Here comes the forces. You would add up these forces. So this was by the virtual work method, this was by the virtually applied loading, and this solution was for the real loading. you will sum up here is basically the length, and you will equate or basically you will multiply the component, you will multiply the component with each, like you have a minus 0.471 minus 5.666 plus 5.666. You will multiply all these to obtain this matrix. So all three values are being multiplied and computed in equivalent truss. So this truss is basically small n multiplied by n into L, which is a multiplication of the response due to virtually applied loading, response due to real applied loading, and length of elements. You will compute these values in a formula and sum it to the all of the member elements. Then you will calculate the deflection at point C. We have this equation. You have a 15 value at for this element, you have a 5.33 value for these elements, and it would be computed as 1.23 value, which is positive. Positive means you have a direction similar to the virtually applied loading, then it means that it is going downward. So 1.25 millimeters of a deflection is observed by the application of these 4 kilonewton loads in a truss. You can solve this example at your own. So here comes the end of this lecture, which was the virtual work method, and we only have discussed the bar elements or trusses in this lecture. In case of any confusion, you can ask questions on my email ID, and you can ask it in comment section. Thank you so much for watching this video. Allah Hafiz.